right. Hello, everybody. This is Professor Iris Miano giving you your Week 8, Day 14, if I'm not mistaken, lecture video on sections 5.1 and 5.2. So we're just starting a new chapter, we're starting a new unit, whole new bag of tricks ahead of us. We are finally starting to get into this idea of proving certain polygons congruent to one another. I know I've been alluding to this a little bit over the beginning part of the semester. Today's the day where we get into that, like fully immerse ourselves, get in their feet first, and then so that's basically the gist of 5.1. In 5.2, we will be outlining a consequence of being able to prove that polygons, specifically triangles, if they're shown to be congruent, then we can go ahead and say some things about corresponding parts that are not necessarily formally stated as congruent. You can go ahead and match them up after the fact. If that was not super clear what I mean by that, it'll definitely be clear what CPCTC is all about. That's 5.2. Okay, so let's go ahead and dive right in with triangle congruency. So the definition of this idea is that two triangles are congruent if all of their corresponding side lengths are equal in length and therefore congruent, and all of their corresponding angles are equal in measure and therefore also congruent. So take two generic triangles, ABC and DEF, as you see on the screen, and they look really super similar to each other, and the word similar is actually going to have a very distinct definition. We'll get to that in chapter 7, I believe. Yeah, is when we get into similarity. Very exciting. So, but in fact, they are congruent to each other because all of their corresponding side lengths are congruent to each other. So that means, according to this notation here with the tick marks, line segment BC corresponds to line segment EF because they each have a single tick mark on the side length itself. So that means that they're matched pair congruent edges. Same is true for line segments AB and DE. They are a matched pair because they have 3 tick marks on each of their edges. And then AC and DF among the two triangles are another matched pair of congruent edges. And then this would be the symbolic notation associated with the congruency symbol and naming these as line segments and all of that stuff. This is how you would represent it using mathematical shorthand notation. And then if you wanted to say that their corresponding angles match up, you would do so with the incorporation of single, double, or triple arcs, or, if you have more than 3 interior angles, like if you're talking about polygons, upwards of 3 edges, quadrilaterals, and so on and so forth, then you'll have more arcs going on in there. But for the purposes of triangles, of course, we just have one corresponding congruent set of angles have a single arc, the other one has 2 arcs, and the remaining last one, in this case, angles C and F, have 3 arcs. So the number of arcs determine which angles are matched up as a corresponding pair. So, and then this is the way you would state these things using, the mathematical symbolic shorthand. And so if you have all of these 6, items, 6 statements in play, then certainly you can conclude that the two triangles are congruent to each other. But do you need to have all of this information in order to say that 2 triangles are congruent to each other every single time? No, actually there are shortcuts, and that's what the 3-letter codes are going to be indicating for us that we're going to talk about in this section. So, but before we get into 3-letter codes, I want to highlight that this relation of triangle congruency has all 3 of those properties that we discuss sometimes when we introduce a new relation. It's reflexive, so any triangle is indeed congruent to itself, duh, right? And then that one's a little bit of a forehead slapper. It's like, yeah, we get it. It makes sense without even having to be explained, hopefully. The triangle congruency relation is symmetric, which is to say that if you have one triangle that is able to be shown to be congruent to another triangle, it doesn't matter in which order you state the congruency between the two triangles. It's the same concept either way. If there are 3 triangles in play and 2 triangles are congruent to the same triangle, then you can match them up through congruency directly. And therefore, triangle congruency has the transitive property. Okay, I don't think there's any place on your lecture notes to actually write that down. I just wanted to make sure that it was stated that this relation has these 3 properties. So you can write that in the margins if you really want to, or you could just kind of be like, okay, noted, and move on. Okay, here we go. Here's some actual content. Postulate 12. If 3 sides of a triangle are congruent to 3 sides of a second triangle, then the triangles are congruent. So this is a 3-letter code for triangle congruency called SSS, right? And it stands for side, side, side. Okay, all the S's always stand for side, A's stand for angle. When we get into other 3-letter codes, that'll be the designated translation of these 3-letter code shorthanded acronyms here. Okay, so this is side, side, side. So here is a generic example of 2 triangles that have side, side, side congruency. Okay, so you can see the 3 matched up corresponding edges that are stated here with the mathematical notation, here with the tick mark notation on the edges, and that's one way that you could conclude that the 3 sides are congruent. Is it true that corresponding angles are congruent among these 2 triangles? Well, sure, it's true, but it doesn't need to be shown in order to use this 3-letter code to justify claiming that the 2 triangles are congruent. So I hope that is landing for everybody. And there's going to be other 3-letter codes that are presented in this section via either postulate or theorem. And so that's my job to present these things to you. But before we get any deeper into 3-letter codes, I want to make sure that this type of justification is illuminated to you, because it's definitely going to become relevant for us. You will find in lots of examples, it will become useful for us to say that either a side length or an angle is congruent to itself or has the reflexive property of congruence. You can shorten this justification by simply saying the word identity. So now we have a little bit of a shorter way to say that something is congruent to itself. And some things that are possible are line segments or angle measures, or angles rather. Measures are equal, angles are congruent. So yeah, if you need to state that the side length or angle is congruent to itself, simply say identity as your reasoning. That's something that you now get to do. So here is a little bit of a generic example. This actually isn't in your lecture notes. It's just by means of illustration on how this identity justification works. So consider triangles TRS and a triangle VRS. Okay, so these are triangles that are overlapping with one another. Okay, so if you'll notice there's a line segment RS that is considered to be the base, the bottom horizontal edge for both triangles RST and RST and SRV. I think I gave them different triangle names when I was generically describing them a moment ago, but there's no wrong way to name a triangle, right, if you guys recall. So you can say that RS is congruent to itself to make a matched pair of congruent edges among these 2 separate triangles that happen to be overlapping. So their overlap is what makes line segment RS present on both triangle RST and SRV. So it's there for both, and so you can use it as a matched pair of congruent edges because every line segment is congruent to itself, right? Okay, now let's entertain a specific example in which we want to use this. So if we have this idea in our mind pretty clearly, then how can we implement it with a specific example? So here we go. Let me read it to you. The triangles to be proved congruent have been redrawn separately. Okay, so look at the 2 figures at your disposal. We have the figure to the left, in which the 2 triangles are resting next to each other and they are sharing edge MP. They've been redrawn to the right such that they are separated from one another, and so MP and MP are two separate edges among two distinct and separated triangles, but technically they're the same aligned segment in the original drawing. So for part A, it says, oh yeah, and in the separated figure, before I even start to say anything about part A, the congruent parts are marked. That's what these tick marks are indicating. So that means that NP and QP are a pair of congruent edges, their corresponding parts, and then NM and QM are a distinct pair of congruent edges. Okay, so for part A, we want to name an additional pair of parts that are congruent by using identity. That would be MP. Line segment MP is congruent to line segment MP. You can make that claim in the process of trying to prove that these two triangles are congruent, and you would justify it by using identity, as that would be the reasoning associated with that particular statement line in a chart proof, okay? Table proof. I use chart and table kind of interchangeably. All right, so that's part B, or part A. Part B is considering the congruent parts, state the reason why the two triangles must be congruent. Well, when they're drawn separately, the corresponding congruent parts are marked, which will be sides NP and QP, right? That's one pair of sides. NM, QM, a second pair of sides, and then MP is congruent to itself. That's a third pair of sides. So the justification for naming these two triangles congruent would be side, 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 as such. Okay, so that's what they were looking for part B. Okay, so this is very early on in this idea of being able to prove triangles congruent. So if you're looking at this stuff and you're just like, I'm not really sure how this fits together, don't worry. There's several example proofs that I'm going to present in this section alone that are going to help us solidify this idea, and for other three-letter codes as well, okay? Case in point, postulate 13 introduces a new three-letter code. You may notice it in bold right away, SAS, but it states in its entirety, if two sides and the included angle of one triangle are congruent to two sides and the included angle of another triangle, then the triangles are congruent, and this is called SAS congruency, or side angle side congruency, okay? You'll notice that I'm using the word congruency after, but you just have the three-letter code. The word congruency is not necessary for you to use after describing, what type of justification you're using to say that two such triangles are congruent. And here are a generic example of two such triangles, okay? Here you'll notice triangle ABC is said to be congruent, right, to triangle DEF by virtue of these particular items being in play. Now, this is not the only way to show side angle side congruent, but this is an example of side angle side congruency because we have a corresponding side BC and EF are congruent. The angle that matches up the other congruent side, which is sides AC and DF, right? That's the other side of congruency. Matched corresponding pairs that we have. Notice that the angle that connects the two pairs of congruent edges is also congruent. That is what is meant by saying the included angle among two pairs of congruent corresponding edges. Since all of that is in play, we can then conclude that these two triangles are congruent to each other. Okay, cool. So what would be a good example of this in proof form? Well, let's go ahead and have an example. So we're going to write up the formal proof for this given and proof statement and figure, okay? So notice that we have two triangles that happen to overlap one another. Can you tell me, this is a rhetorical question because you're watching a video obviously, but what edge appears to be occurring for both triangles, RST and SRV? It's this bottom one right here. It's not always going to be the base, that's the shared edge, but in this example, line segment RS occurs in both triangles RST and SRV. So at some point over the course of this proof, we're going to match them up as a congruent pair of edges among the two triangles, and that's going to give us one of the sides that allows us to claim triangle congruency among these two triangles. And that's exactly what we're trying to prove here. Notice the proof statement is triangle RST is congruent to triangle SRV. How will we get there? hint, 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 spoiler alert, it is going to be through SAS congruency, side angle side. But let's arrive there together, okay? So it might be helpful, notice what I've done is I've put tick marks and a single arc, a single tick mark and a single arc in the interior or edges of corresponding congruent parts that are given to me here, okay? It's always a good idea, and I highly encourage that if you're given some corresponding congruent parts in the process of writing up the proofs in this section and, you know, the ones ahead, that you mark them in your figure, okay? So this tick mark, just to be clear, is meant to indicate that the entire line segment from T to R, right, TR, is supposed to be congruent to VS. Now, that's not to say that it's just from S to this unnamed intersection point. It's meant to indicate the entire edge. So hopefully that's clear enough, okay? And then furthermore, angle TRS and VSR are the interiors of these angles in which I have the single arc in each of those instances. Okay, so then watch this. I'm going to throw all of that given information as the first statement and say that the reason that I get to claim this is that it's given. This is always your first move when you're writing up your table proofs. Always your first line is put the given information in as the first statement and say that it's given. That's your freebie. From there, I'm going to look at my figure and recognize that RS is the base of both of the triangles at the same time. So I'm going to say that RS is congruent to itself via identity. That's the justification. Anytime you need to say something's congruent to itself in the process of proving triangles congruent, this is your go-to. This is the structure. This is the reason you get to use. And that gives me another edge, another side, right? In the side angle situation that's already in play from the given information. Let me add 2 tick marks to that edge, indicating that it's congruent to itself, right? And that'll give me the ability to make the proof statement happen. Super short proof here, right? It's a 3-liner, which is something that earlier some students were like, oh, I'm used to these, you know, geometry proofs in general being short, usually 3 lines. Here's a case in which it's 3 lines, and it's warranted to be 3 lines, and nothing wrong with that. There's no way that I can see making it any longer. Why would you want to, right? So yeah, we're ready to make the proof statement here, and we can justify it with side angle side, which came to us as a postulate, right? So it's something that we get to use right away whenever we can establish it. And the only thing we had to do was recognize that the bottom edge of both of the triangles overlapped, and so it's congruent to itself. And that gives us another side to be able to say that this triangle RST, so that's this kind of, I guess you could say, rightmost triangle, is congruent to the left triangle that it overlaps with via side, angle, side. Did you see me tracing my cursor over it? Let me do it on the other triangle. So that was triangle RST, so triangle VSR, or SRV, sorry. Can't misname a triangle though. Any name is totally valid. But this other triangle has the side, angle, side, right? Congruence, a relationship with the other triangle. So that's what makes them congruent. So this is another instance other than side, 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 where it's like a little bit of a shortcut from having to show that every single side length corresponds to every single other side length among the 2 triangles and also the angles. You don't have to show all of that. You can just show side, 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 or you can show side, angle, side, as indicated by this proof here, okay? Now, moving on to the next postulate, 14, angle, side, angle. Yeah. Specifically, it states, if 2 angles and the included side of one triangle are congruent to 2 angles and the included side of another triangle, then the triangles are congruent. Angle, side, angle congruency. Now, what does that look like in a proof? Here's an example proof, right? Wait, hold on. We're not at the proof yet. This is the generic example, and then we're going to have a corresponding proof that uses this in order to prove it. Okay, so here we go. What have we got? Oh, look at this. Angle, angle. Angles A and D are congruent to each other. Separately, distinct to that, but also related. Angles B and E are congruent to each other. And notice that the side that joins together those two pairs of congruent angles, right, the included side, is also congruent among the two triangles. That's side length AB and DE here. So if you can establish all of this in two triangles, then those two triangles can be shown by use of this postulate that they're congruent to each other. That's enough information to claim triangle congruency, angle side angle. You can use it. Here is a proof that will, spoiler alert, use angle side angle as justification ultimately to make the proof statement happen. Specifically for this proof, it'll be that triangle PQR is congruent to triangle NMR. Now, what are the pieces of given information here? We have that PN bisects MQ and that angles M and Q are right angles. Okay, so how can we use this information in order to make, we're going to make a pair of sides congruent to each other using the first piece of given information, and we're going to link together a pair of angles as being congruent to each other using the second piece of given information. Let me highlight this to you formally. So first off, take the given information, either the entirety of it or just one statement of it, and say that it's given. Okay, I like to put all of it, just dump it all in the first statement and say, okay, the whole thing's given. I can use any piece of it that I want in order to make my next claim after that. So watch this. I'm going to choose to use that first piece of given information, that PN bisects MQ, to say that MR is congruent to RQ, using the definition of a line segment bisector. So a bisector, right, that cuts for a line, by definition, and you can take apart the word to figure out what it does. It bisects it, which means it cuts it. Sect means cut, bi means two. So it cuts it into two equally sized pieces. Equal measures are congruent. That's how I'm making this claim here in statement 2. And you can add some notation to your figure in order to indicate this. By that I mean, of course, the tick marks. There they are. So be careful with this because you want to make sure you're bisecting the correct line. It would be incorrect to say that based on this first piece of given information that NR is congruent to PR, because PN is the line that's doing the bisecting. It bisects MQ, so MQ is the one being cut in half, not PN, just so that we're clear, okay? Because it can be a little tricky, like really picking apart the language to know which line is being cut. And that'll indicate which line segments subsequently you can say are congruent to each other by virtue of using the definition of this term bisect. Okay, great. Now we are ready to claim that, guess what? Angles M and Q are congruent to each other, right? This might seem terribly obvious and like something that you don't need to explicitly state. You do though, because you actually have to have those two angles as a congruent matched pair. You need to state that they're congruent to each other unless they're already stated as congruent for you, which they're not. Notice the given information is just that they are two right angles. Now, since they occur in two separate triangles, and we know that all right angles are congruent to each other, we can then use that information. Literally, I put in my reason for saying that angles M and Q are congruent to each other, that all right angles are congruent. I know, this was a theorem that was presented ages ago, that if you recall when I first introduced it to you, I was like, this one seems like so dumb. Like, why would we need to ever use it to say that right angles are congruent to each other? Here's a case in point. It was presented that these two angles M and Q are right angles, so we can use this theorem to link them together as a congruent pair of angles among two triangles, and this is going to help us with our proof. So now we have an established set of edges, sides. We have an established set of angles. Now we either need another edge like that includes the angle, or we need another set of angles that includes the edge that we already have. And check out angle MRN and QRP, right? Ooh, I even said them in the right order. Sweet. So I had the same thought process as I do right now as I did when I wrote this up. So I'm going to go ahead and let them be a pair of congruent matched angles. And what allows me to do that? Well, notice that they're in vertical positions. They're in opposite positions of one another, when these two lines MQ and NP are intersecting. And we know by theorem that vertical angles are congruent to one another. So that's what I'm using as justification to match up those angles, right, as another congruent pair. And notice among the two triangles now, I have angle, side, angle, angle, side, angle. So that ASA, right, ASA, is going to be justification for making my proof statement happen. I now have enough information to claim that these two triangles are indeed congruent. Angle, side, angle is enough. You don't have to show all angles and all side lengths. That's overkill, right? You just have to show either side, 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 angle, or angle, side, angle, as we just saw in this specific example. Now, there are other combinations of A's and S's out there, and you might be wondering, well, are all combinations of A's and S's in those three letter code possibilities, are they all valid for proving triangles congruent? No. There's going to be some that do not work out. And the one that's ASS, angle, side, side, that is a no-go, right? So I like to make this statement to help students remember that you do not want to mess around with ASS in trying to claim that it is justification for proving triangle congruency. It is not. And the textbook has a really good figure associated with illustrating why it doesn't work out. Okay, so here, and I believe on the lecture notes, I ask you, what figure illustrates like why you can't use ASS for triangle congruency? It's figure 5.9, which I have scanned on the screen here for you. Okay, so I just wanted you to be able to remember like where to find it, what figure number it was. Anyway, so let's take a close look at this figure here. We have triangle A and triangle B. And you may notice that triangle A has a pair, 2 unit long, edge and a 5 unit long edge that are touching, and then a non-included angle of 20 degrees here. Notice triangle B has exactly those same features, but the included angle among the two triangles between the two corresponding edges, the 5 unit edge and the 2 unit edge, they're clearly different among the two, right? Like the angle between the 5 unit and 2 unit edges is acute for triangle A, but the angle that matches those two 5 unit and 2 unit edges is definitely obtuse, or maybe it's close to 90 degrees. I would say that it looks like it swings a little bit further out from 90 degrees, so I would say that that's likely obtuse. Are acute angles and obtuse angles ever able to have the same measure? Well, no. By definition, acute angles are something that measure less than 90 degrees, and obtuse angles measure greater than 90 degrees. Can you be less than 90 degrees and greater than 90 degrees at the same time? No, you cannot. So that means that these two triangles, while having side-side angle, side-side angle corresponding congruent parts, they are clearly not congruent to each other, okay? Furthermore, this edge that doesn't have any measure to it, right? It doesn't have like the tick marks on it, to indicate 2 units, 5 units. We don't know how many units either one of these are, but they clearly are not congruent to one another. Furthermore, this other third angle, one is acute and one is obtuse. So it's like, not all of the parts correspond here, so we cannot claim that these two triangles are congruent. And that's why angle side side does not work. And if you try and be clever and just like rearrange the, the order of the S's and A's such that it's side side angle, that's still like two sides with a not included angle, right? That's still representing the same type of idea. So do not mess around with ASS or SSA. These two configurations of corresponding congruent parts do not lead to triangle congruency, okay? And here in figure 5.9 is one case in point. It's the case, like it's a counter example, right? So it only has to be shown that it doesn't work one time to convince us as mathematicians, geometers, that We're not going to rely on this as a mechanism for proving triangle congruency, okay? Are there any other combinations of A's and S's that don't work? Well, yes, and that's AAA. Now, AAA, or angle, 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 is not a congruency mechanism. It is, however, a similarity mechanism, and it actually, PS, gets shortened to just AA. It turns out you only need two corresponding congruent angles in order to show similarity. We'll get into that into chapter 7. Like, you know, put a pin in it for now, but it's also a mechanism by which you cannot claim congruency. Here we go. And so here is the textbook illustrative figure that kind of shows that. So notice that we have two, triangles. One of them is actually inside of the other one, which lets you know that they congruent be claimed to be congruent to each other, because obviously we have what would be corresponding edges, not congruent to one another. Otherwise, if they were congruent, we would not be able to fit one inside of the other with room to spare, right? Everyone's okay with that? But they do have corresponding congruent angles all the way around. And that is something that is valuable to us when we talk about triangle similarity. And we'll find that there is a relationship between the corresponding side lengths and that they're proportional to one another, as you can see here. So yes, it's not a 3-letter code for congruency. We're not going to use it right now, but we are going to use it later when we talk about similarity, because you will notice, even if you haven't yet been formally introduced to the definition of similarity as it pertains to polygons, hopefully I can say with some clarity and understanding with everyone that these two triangles that you see in figure 5.10 are similar. Indeed, I think everyone would agree with that. Moving on. Here is our first theorem of this section. In fact, I think it's the only theorem that's presented in section 5.1. And so it's something that we're going to prove together. And it is another 3-letter code, AAS. Yes, you can do AAS. You cannot do ASS, though. ASS, that is a 3-letter code that does not lead to triangle congruency. AAS, or SAA, although no one does it in that order. The convention is to have it angle, angle, side in that order. This is when you have two corresponding congruent angles, but with a non-included side. And if this happens among two triangles, then that's another way you can prove triangles congruent. Here is a generic example of that using the same triangles ABC and DEF that we've been using all, section long in this lecture video. And if the corresponding parts look like this, you can certainly prove that the triangles are congruent. So let's go ahead and prove this theorem together so we can use it in homework exercises outrightedly, just like a postulate, okay? So let's go ahead and, I can't remember if you guys are given the given and prove statements, or if it's your job to write them as part of the exercise. And in the event, take a moment if you need to write these down. Let's say in the process of proving this theorem, writing up the formal proof for it, that the given statement would be angles C and F are congruent, angles B and E are congruent, and line segments AC and DF are congruent. So then we want to use all this information to prove that the two triangles are congruent. Now watch this. We're going to dump that first statement with all of the given information, dump it right in there, and go ahead and justify it with the word given. That's your freebie, right? Always it's going to be like this. So where can we go from here? Okay. Well, it's a little bit obscure, but if you recall, it was already presented to us that when two triangles have two pairs of congruent angles, then the third angles are also congruent. That's the theorem we're going to want to use in order to claim that angles A and D are congruent. Okay, and go ahead and add 3 arcs in the interior of those two angles in order to indicate this fact in the figure. Now we can use one of the postulates that's already been presented in order to make our congruency claim among the two triangles, and it would be angle side angle, because here would be your angle side angle, angle, side, angle. Like you should be able to trace, that certain portion of your triangle with your finger to like find all of the things in the 3-letter code that you're using as justification. So that's one rule of thumb that I use in order to, convince myself that I'm using the right 3-letter code. I can elaborate more on this and anything from 5.1 in class, but for now, let's go ahead and move on to section 5.2, which is called corresponding parts of congruent triangles. So now that we know how to prove triangles congruent, what is a logical next step that we could take after that? And it would be that we can prove that other corresponding parts that were not part of the original conversation, as long as they correspond according to the triangles being proved to be congruent, they can also be shown to be congruent as well. So that means, for instance, just going back to this example real quick, I can, once these two triangles are proven to be congruent, like let's say, we're here with it, let's say that the proof statement was that I needed to prove that line segment AB is congruent to line segment DE. Well, then I could make that claim right after this third line and say that corresponding parts of congruent triangles are congruent, or CP-CTC. Oh, I know, that's a mouthful. It's not easy to say it all the way through correctly when you need to, when you're first learning this. It doesn't roll off the tongue very well. Yeah. So what mechanism can we come up with to memorize this? Now, students come up with all sorts of fun ways, but yes, we need to memorize corresponding parts of congruent triangles are congruent. So if you memorize that phrasing, it's the first letter in each of the non-trivial words in that phrase. Or you could do what one of my students did in a summer class that I taught. He was so funny. He in his brain, he came up with the fact that saying CPCTC matches up with like the melody of like the conga dance. CPCTC, hey, CPCTC. I don't know. So he would sing it to himself like that, and every time he needed to use it, like in some proofwriting or some exercises and homework, he would say CPCTC, hey, CPCTC, and it was helpful for him. So if that works for you, use it. If you come up with your own way of memorizing the order of letters for CPCTC, corresponding parts of congruent triangles are congruent, and you feel comfortable sharing that with the class, by all means, I would be delighted to hear this. I always like to have new, fun ways of memorizing monotonous bits of information like this. It would be very helpful to me in future, teaching endeavors, and also to the entirety of your class, like all of your classmates, I'm sure would enjoy and appreciate another way to memorize this acronym, because it's, like I said, it's not super intuitive for sure. It's a new clunky piece of information, I would say. Okay, now when would we need this? How would we use this, right? Let's go ahead and dive right into an example proof. And so here we are given this figure, of course, which is two triangles that have a shared vertex of M, it looks like, which happens to be the intersection of line segments PR and NQ. So that's just what we gleaned from the figure. The given information specifically says that M is the midpoint of NQ. So we're going to be able to use the definition of midpoint to say something definitive about NM and MQ, giving you a little hint there. So that's going to be like something that we springboard off of this first piece of given information. Next, NP, that's this edge right here, and RQ are said to be parallel with transversals PR and NQ. That's going to be huge. We're going to be able to make a couple of claims about certain angles being congruent to each other by virtue of parallel lines being cut by transversals. Remember that whole thing with chapter 4. So that's going to be, definitely something we want to be able to clearly reference from our past. And we want to eventually match up line segments NP and RQ, those parallel lines that were mentioned, we want to be able to say that those line segments are indeed congruent to each other. So we're going to wrap this particular first proof up with a CPCTC. Hey, okay, so it's coming. All right, but let's put it all together. So here is the beginning of our chart proof. Always, you're going to want to have at least the, one of the given statements as the first statement. I just plop them all in there. And by all, I mean two. There's two statements here, technically. And just say it's given. I usually use the pieces of given information in order, like the first thing is usually my first jumping off point. So I'm going to use the definition of a midpoint to claim that line segments NM and QM are congruent to each other. And I'm going to add tick marks to my figure in order to indicate that. Okay. Furthermore, I'm going to use the parallel lines with one of the PR or NQ being transversals to make a claim about angles. I guess I went N and Q with it, okay? So N and Q are alternate interior angles with transversal NQ, okay? So there's that, me making that claim, and I'm going to go ahead and add arcs inside of the interiors there. So if that needs a little bit more explanation, if we want to like extend these edges, that can be helpful in seeing that these angles N and Q are actually alternate interior angles, okay? So don't be afraid to add some extensions to those edges in order to make that clear for you, okay? Now there's a couple of different ways you can move forward with this next bit. Okay, so I'm going to click forward and we'll talk about what I have prepared here, and then we'll talk about the alternative way as well. Okay, so it looks like I used the other PR being the transversal to say that angles P and R are actually a matched pair of alternate interior angles. Okay, so I'm going to put two arcs inside the interior of those angles in order to match them up as a congruent pair, and that'll allow me to say that triangles MNP and MQR are congruent to each other by virtue of angle, side. Okay? Now that I've shown you how those triangles are congruent, I want to, before I finish this proof, which P.S. I'm not finished with it because remember, the entire point of it was trying to make NP and QR line segments as a matched up corresponding congruent pair of edges. I'm not there yet, but I will be able to make that claim in the next line with CPCTC. What I wanted to point out is that instead of saying angles P and R are congruent, I could have just as easily said that angle NMP is congruent to angle RMQ by virtue of being vertical angles, and we know that vertical angles are congruent. Then I would have been able to say that the two triangles are congruent by angle, side, angle. You see what I mean there? Like there's a different way to move forward with getting to triangle congruency for this particular proof by virtue of what's been given to us, what the context is here, okay? So it's an alternative way. It doesn't take into account this PR being a transversal for the parallel lines NP and RQ. So in that way, I feel like maybe it's not the intention of the author to go in that direction with the proof writing, but it's not incorrect, like at all. It's totally a valid alternative write-up for this part of the proof. But put a pin in that and just say to yourself, let's just finish this proof. And we're ready to make our proof statement. Now that the two triangles are said to be congruent to each other, we can claim that these edges NP and QR are congruent because they are corresponding parts of congruent triangles. So they must be congruent. CPCTC. Hey, CPCTC, right? The triangles were shown to be congruent in the fifth statement. We proved it. We did it with angle, side. We could have done it with angle, side, angle, as I described earlier. Once two triangles are congruent, any other parts that were not explicitly shown to be congruent by the process of proving that the two triangles were congruent can then be claimed, can be matched up as congruent to one another as long as they do indeed correspond. Okay? So NP clearly corresponds, that's the counterpart, in the other triangle that matches up with RQ. Okay? Cool, 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 cool. So hopefully that all makes sense and is good to go. If we need more conversation about it, that's what class time is for. So I look forward to anybody wanting to talk about this or any other proof in more detail. Let's go ahead and move on to the next thing. All right. Ooh, so in this particular section, we have a little bit of a conversation that we need to have in regard to right triangles. And we have a special 2-letter code in order to help us along with proving specifically that a pair of right triangles are congruent. So that's fun. Watch this. So let's define right triangles in a manner of describing its side lengths. So right triangles by definition have a hypotenuse and 2 legs. So here's a generic right triangle. Notice that it doesn't have any vertices noted, but it does have a right angle in its interior, and that's what makes it a right triangle. So it has a hypotenuse, which is always the edge opposite of the right angle, and then the other 2 edges are just generically both called legs. The legs could be equal to each other in measure. They could not be equal to each other in measure. That doesn't matter at all, but they're just legs because they're not the hypotenuse. Either, as far as edges are concerned, either you're the hypotenuse or you're a leg, okay? So there is a special method for proving that right triangles are congruent, and it's called hypotenuse leg, or HL. So this is a little 2-letter code, and it's only for right triangles. So if the hypotenuse and a leg of a right triangle is congruent, then the hypotenuse and leg of another triangle, then the 2 triangles are congruent. And I know you might be thinking to yourself, oh, the hypotenuse and a leg along with this angle, that's angle side side. And you told me angle side side wasn't okay. Turns out it's okay, but only for right triangles. And hypotenuse leg is the thing that allows you to get there without having any trouble. You're not going to be putting ASS or SSA and try and be sneaky about it. It's only for right triangles. And so the correct code for justification in using this particular concept is HL, or hypotenuse leg. Here is an example proof. Spoiler alert, this is going to be HL at the end, okay? We're going to prove that triangles RST and VST are congruent to each other, and you may notice a couple of things, that they're both right triangles. We need to claim this. We need to actually explicitly state this as a jumping off point from this first piece of given information. And you may notice that even though there's these corresponding side lengths VT and RT that are said to be congruent by virtue of the second piece of given information, you may notice that these 2 triangles also share an edge, don't they? What edge do these 2 triangles share? ST. Okay, so we'll get to that in a sec. So that's going to help move along our HL proof in order to eventually prove that these 2 triangles are indeed congruent. Watch this. So obviously dump, at least in part, your given information into the first statement and then say that it's given. From there, categorize these 2 triangles as being right triangles. You need to explicitly state this if it's not already explicitly stated, in order to eventually use HL, because HL, or hypotenuse leg, is explicitly for right triangles. You cannot use this for any other kind of triangles except for right triangles. So explicitly stating in your proof that you're dealing with right triangles is paramount. It's very important, okay? So I'm going to explicitly state that these 2 triangles are right triangles because, and I'll put generically definition of a right triangle. It's a triangle that contains a right angle. So if you want to actually put the definition, that would be the wording. You would say right triangles are triangles that contain a right angle. Boom. Okay? Next, let's go ahead and use that identity or reflexive property of congruence, if you like, in order to say that ST is congruent to itself. That makes another matched pair of edges, and it happens to be the hypotenuse of both of these triangles here, okay? So at this point, we have the hypotenuses matching up, a leg for each triangle matching up, and they're both right triangles. We can go ahead and make our proof statement happen, and HL, simply HL, is the justification for that. It's hypotenuse leg, which states that for any 2 right triangles, if you can show that the hypotenuses match and a pair of legs match, that's enough information to say that those 2 triangles, right triangles in particular, are congruent to each other. And that's that for that one. Again, and always, let me know if anything that I present in any of these lecture videos is unclear. Good use of class time to address it so everyone can get on the same page, okay? Moving on. Ooh, Pythagorean theorem. Yeah. So this is something that I'm sure everyone has already been introduced to, and if you haven't, don't worry. I'm here to formally introduce it to you, start to finish for sure. The Pythagorean theorem states that for any right triangle, if you, it makes it a little easier if you represent the side lengths as some either known or unknown values. In this case, we're going to let one leg, a line segment BC, take on the value of A, lowercase a. Line segment CA is taking on a value of lowercase b, unknown to us, and that's fine. The hypotenuse, or line segment AB, is going to be represented algebraically by a lowercase c. So the square of the hypotenuse is equal to the sum of the squares of the legs. That's the Pythagorean theorem, and it's true for every single right triangle. It is not true for non-right triangles. Okay, Pythagorean theorem is only a consequence of right triangles, and that is it. So don't try and push this on triangles that you either don't know if they're right triangles or if they're definitely not right triangles. It is not appropriate to implement the Pythagorean theorem on non-right triangles. Okay, just so we're clear. Here's a couple of examples, real quick style, and then we're done with this lecture video. Almost done here, guys. All right, so let's entertain this generic right triangle with not even any vertices technically shown. We just have side lengths, lowercase a, b, and c respectively. For each of these two examples, I, or 1 and 2, lowercase Roman numeral 1 and 2 there, I and II, we're going to have 2 of the 3 values given to us, so it's going to be our job to calculate the missing value. For the first example here, we have legs A and B having units of 12 and 5 respectively. So that means we're going to be making a point to put them in the A and B positions of the formula correctly, right? We're not going to accidentally put 12 or 5 in the C position, because C is always designated as the length of the hypotenuse, and that's always alone on one side of the equation for the Pythagorean theorem. If you accidentally put, your C value in for A or B, or vice versa, you're in trouble. Okay, so make sure you're plugging in the values into the correct positions when you use the Pythagorean theorem. And then go ahead and use your algebra brain and simplify. And once you get to just a number equal to c squared, if you're indeed solving for c, which we are in this case, you can take the square root of both sides, but only take the principal square root, right? You're not going to take the negative square root, even though technically, right, algebraically speaking, the value of c in this first example is both plus or minus 13. Obviously, we're only going to take the positive one because the hypotenuse value here in this context is a length, and lengths are always positive values. So only take the principal square root. And if you happen to have your c squared or whatever squared value that you're trying to solve for, it's happened to be equal to a perfect square number, then the square root's going to be, a whole number, and that's always nice. That might not always be the case, and because I don't require or allow you guys to use calculators in this class, just make sure that you are able to simplify any non-perfect square number square roots. And so here for part 2 is one such case. So go ahead and set up your A and C values accordingly. So B is the thing we're going to be solving for the second example. So you're going to square the 7 and get 49, you're going to square the 8 on the side and get 64, and eventually solve for b squared in the following way. So here, from step 1 to step 2, I just squared the 7 and the 8. From step 2 to step 3, I subtracted 49 from both sides, and I got b squared equals 15. 15 is not a perfect square number, right? And it doesn't have any perfect square factors. So in order to find the square root of it, you simply take the square root of both sides. And so b equaling the square root of 15 is a perfectly acceptable final answer. Just for fun, I put the decimal approximation for that. But that's not something that you are expected to calculate by hand. Oh, Lord, no. Don't do it. So just leave it at square root 15. I just put that decimal approximation, rounded to the nearest hundredth, in there for fun with the squiggly equals, okay? It's not something you're expected to produce, okay? And if you do produce it on a graded event, I'm going to know that you had access to a calculator, and that's going to be not good, okay? So don't do it. Don't do it. All right, I believe that's it. Yep. So here is where I remind you that there are selected homework problems from your textbook that I want you to practice. That'll be fair game material for the upcoming quiz that's going to be covering these sections. And certainly it's good fodder for exam, questions once we get around to a Unit 3 exam. Cool, that's it. Thank you so much for your attention. I will see you soon in class. I can't wait to discuss these sections with you. All right, take it easy, and I will see you soon.